Hey everybody, and welcome to NASA Science Live. I'm Molly McKinney, one of your co-hosts for today, as we join you from the Hampton Roads Convention Center right here in Hampton, Virginia, and cover day one of the 2021 Moon to Mars Ice and Prospecting Challenge brought to you by NASA. What's going on behind me? Why don't you all take a look? Students have gathered from 10 different universities across the country to test their original technologies to solve a lunar and Martian exploration dilemma, which is how to access subsurface ice and then melt that ice into water. Why is this important to NASA? Well, as we look forward to the Artemis program to the moon and even one day crewed missions to Mars, being able to access resources like water will be crucial for humans to survive on other worlds. So teams have been tasked with designing an ice and water harvesting system for use on the moon or Mars. Not an easy task. And today they're testing their systems out in a head-to-head competition. Now we are in person this year. We've jumped through quite a few hurdles to make that happen. And we are following very strict COVID protocols to make that possible, including everyone on the floor wearing face masks. We are all fully vaccinated, or we've had proof of a negative COVID test in hand. Now, if you have any questions throughout the show today, you can send them in using the hashtag AskNASA, or you can leave a question in the comment box wherever you're watching from, and we'll try our best to get those answered for you today. It is a live show. That's one of the many perks of it being live. Well, I'm sure you can hear the excitement in this room. This is a real live show, so there's drills happening as we talk. But before we get into the competition, why don't you step over here, and I'm going to explain a little bit more of the process so you can understand how the Moon to Mars Ice and Prospecting Challenge works. So you'll see these blue bins at each one of the team stations. And situated at the very bottom of these bins is a block of water ice. Now, the objective of this challenge is for teams to get their drilling apparatus or their drilling system all the way down to that water ice, and they're supposed to extract water from the ice. That's where these buckets come into play. You'll actually see water funneling into them. What's tricky about this challenge, if that's not hard enough, which that's hard, is hidden underneath is this word called regolith. You'll hear it getting tossed around quite a bit today, and it's actually simulated lunar or Martian terrain, because let's face it, on the moon and on Mars, we may not know what the soil is like underneath the surface. So teams have to be able to, as they're drilling down, collect data to put together a digital core. So if you think of a core sample when you pull it out of Earth, you see all these different layers of soil. So teams have to digitally gather how many layers they are, how thick the layers are, and how hard they are. Some layers may be really soft, some may be hard, more like a cement consistency. So it's a really difficult challenge for these teams, not to mention keeping in mind weight specifications and different dimensions that they have to focus on. So someone who can tell us a little bit more about why this technology is important into space is the special guest that my co-host Natalie Joseph has over the correspondence desk. So Natalie, let's take it over to you.
Thanks, Molly. Hi, everyone. I'm Natalie Joseph, your co-host for today's Moon to Mars Ice and Prospecting Challenge, coming to you live from the Hampton Roads Convention Center. And let me tell you, you can just feel the excitement in the air as teams work diligently to extract water from these bins. I'm so excited because I'm joined by Alejandro Pensado, an aerospace engineer at NASA Langley Research Center. Thank you so much for joining us today, Alejandro.
Oh, thank you for having me.
Yes. So I understand that NASA is returning to the moon. Can you tell me more about this exciting endeavor?
Yes, of course. This is all part of the Artemis program. We're returning to the moon after 50 years of robotic exploration. This time with a sustained presence there. We're partnering up with industries in ways we haven't done before, and ultimately setting a precedent to keep expanding human exploration.
That is so exciting. So how does the Moon to Mars Ice and Prospecting Challenge help us achieve this goal of returning to the moon?
So we are going to the South Pole, somewhere where humans haven't been there before. And so, for example, one of the challenges is we don't really know what the surface and subsurface are made of. So one of the challenges that they're facing here is being able to demonstrate the capability of creating a digital core to identify the layers as they drill into them. And that's going to be a very useful capability that we'll need to use to explore the moon.
Mm-hmm. And why is NASA interested in harvesting water on the moon and Mars?
Being able to harvest water on the moon and Mars goes a long way for human exploration. There are multiple ways you can use it. It can support the day-to-day operations of humans in those locations, and you could use it to as fuel, a propellant. So ultimately, having a sustainable presence in these locations, water is going to be essential.
And we keep mentioning water. So what do we know so far about water on the moon and on Mars?
So for both Moon and Mars, we've been studying what is there for quite some time now. For the Moon, there's been orbital missions that have identified water on the Moon, and more recently with an L-Cross impact mission, identified that there's water on the permanently shadowed regions of the Moon. Similarly for Mars, there's orbital missions that have identified water, and since the Phoenix lander, we've been learning more and more about the water on Mars. Recent discoveries have shown that there might be large ice deposits beneath the surface, which makes this competition very important.
I bet. And tell me a little bit more about this thing called in situ resource utilization. What is it, and why is it so important?
So in situ resource utilization, or ISRU, is essentially looking at being able to use resources on site. So you can imagine that as we're going to be doing these more ambitious missions, we're going to be needing more and more of everything, propellant, consumables, and this is going to be more of a challenge in terms of if you have to bring everything from Earth. So then the question stems, can we use things that are on the Moon and Mars? And water being one of the crucial items that if you could use it, then you could be helping how things go in terms of the operations and potentially for refueling. So you can imagine you're lessening the challenges of having to take everything there. And similarly, maybe you can start making some design changes based off if you can use things that are already there. So ISRU ultimately gives us a lot of flexibility on how we can design these future missions.
Yeah, thank you. And something that I think, Alejandro, is super cool about this challenge is it's all about students and getting their ideas. So how can students, why is it important that we engage with them, and how might we use these students' ideas in the future?
So it's going to the Moon and Mars is going to be a challenge that we're not going to solve today or tomorrow. And in this long endeavor, it's important to engage with the students early on, because ultimately having them aware of what these challenges are, getting their ideas on these things will be critical, as they will be the ones that kind of answer these challenges down the line.
Yeah, and I've got a chance to kind of look around and I see all these really cool drilling systems, and people are already getting some water, and it's super exciting. Have you had a chance to walk around and take a look at the designs? Is there anything that stands out to you?
Yeah, it's very exciting to see the designs in action. It's very interesting to see how they've been refining and working off of ideas from previous years. You can see that they all have their kind of unique design choices on how they did like the structural systems and so forth. And then they're still doing some interesting trade studies where how do you extract the water in terms of a liquid form or a vapor. So they're getting a chance to test all these ideas, and I'm excited to see how they come out.
Well, thank you, Alejandro. We actually have some questions coming in from our hashtag AskNASA, and you can submit your questions. Just use that hashtag AskNASA. So, Alejandro, Emily on YouTube asks, are there any future plans to launch to Mars from the Moon, since the Moon's gravity, well, is much smaller than the Earth's?
So that is part of a trade study that is being conducted. Obviously, there are benefits into using a lower gravity well as a launching point, but there's so many pieces along that way that we're still trying to figure out the benefits and how we can go about that.
And Brittany on Twitter asked this question. I love this question, Brittany. Is it really safe to drink Martian or lunar water?
So the answer is carefully. This is going to require pushing the technology to make sure that we can process it. There will need to be a filtration system. So I will go with a maybe.
Maybe. Okay. We'll see. So we have one more, our final Ask NASA question for you, Alejandro. And Scott on YouTube wants to know more about the new Viper mission that will scout for water on the moon. And actually, Scott, we just selected the landing site for the Viper rover on Monday. So that's a great question. I love this. So Alejandro, can you tell me more about that and how the Viper rover ties into this competition today?
Of course. So yes, the landing site was recently selected. It was selected for the Nobile region near the South Pole. So one of the challenges is we know there is water there, but we don't know exactly in what concentration and distribution is there. So Viper is going to answer those very questions and give us a better idea of kind of a resource mapping. And based off that, it'll give us a better idea of how we can extract the water from those areas, which is in turn going to guide us in how we can develop these ICU technologies that you see today.
Great. That's so exciting. I am really, really excited about all of these missions we have going on at NASA. So Alejandro, thank you so much for joining us today.
Of course. Thank you for having me.
Now, Molly has some exciting things to show you all out in the pit. But first, let's learn a little bit more about NASA's upcoming Viper rover.
We know from decades of study that the moon has water, but where and how much? In 2023, a robotic rover will explore the moon's surface in search of water ice. NASA's Viper moon rover will perform the first resource mapping mission on another world, using advanced instruments and tools to determine the location and concentration of water on the moon.
To send Viper to the moon, we're leveraging industry as part of our commercial lunar payload services program, a program designed to send science instruments and technology payloads to the surface of the moon. Viper represents a very different development paradigm. We are developing each instrument for launch on Eclipse ahead of Viper, totally flipping on its head how we normally do this. This is truly creative. An industry partner will launch Viper to the moon's south pole. This is a place where no human or rover has ever been before.
The rover's survey will provide scientists with the most detailed view of the moon's water to date and point to spots where water could be harvested by future astronauts.
Viper will be the first resource mapping mission on the surface of another celestial body. It represents a new kind of mission for NASA in which the objectives of advancing science and human exploration are closer than ever. The measurements that Viper's instruments will make can help us understand the source and distribution of the water and other volatiles on the moon, giving us insight into the evolution of the moon and the Earth-Moon system. The moon's water is also a precious resource that could be extracted to support human exploration of the moon and beyond. What we learn from Viper will bring us a step closer to developing a sustainable, long-term human presence on the moon.
Go Team Viper. We are proud of you all. Looking forward to it. For those of you just joining us, we are coming to you live for NASA's coverage of the 2021 Moon to Mars Ice and Prospecting Challenge. Now, as you look around the pit area today, you'll notice that each of these teams have a different design that's really unique to that team and to that university. Each team brings a different idea to the table, and that diversity of ideas that we get from, including students in a competition like this, really helps us expand our collective understanding, not just for NASA, but really as a global science community. Now, this is the 5th year of this competition, and every year we really learn something new. What worked, what didn't work, and this collective knowledge from student-led ideas can really pave the way for future crewed missions to places like Mars and the Moon. Today is day 1 of this year's competition, and teams are operating their systems for the first time. I was talking to a couple of the teams yesterday, and these systems had never traveled before. So it's always a little nerve-wracking powering these on for the first time. Most of the university students today are using a drill to dig through the simulated lunar and Martian soil to get to the ice below it. And along the way to the ice, teams have to collect data about the layers they're drilling through, how many layers there are, how thick they are, how dense they are, and they'll use this information to create a digital core that they'll be judged on at the end of the competition. And then to extract the water below, teams have converged upon a strategy of melting a pool of ice underneath the surface and pumping it out. rather than trying to extract the ice from the overburden layers up above. Yep, okay. So now that you all understand a little bit about the competition, let's go talk to some of the teams out here on the floor. Our first one up here is from Stevens Institute of Technology, and you made it easy for me. I don't even need the cue card for this one. Steven, nice to meet you.
Nice to meet you.
So tell me a little bit about your design and if you modeled it after anything.
Sure. So that is the extractinator. Very much like a 3D printer, we're able to translate our drill and extractor back and forth, forward and back, and up and down using stepper motors. Our drill is a commercial off-the-shelf rotary percussion drill, which has a 1/2 meter long drill bit. While we're drilling through the overburden layers, we use system telemetry to map out our digital core. So we're measuring things such as weight on bit, feed speed, RPM, current, voltage, all of that. And that goes into our MSE calculations, and we can calculate the hardness of each of the layers. After we're done creating our digital core, we retract the drill, move the extractor over, and lower it down into the hole. We use a 750 watt cartridge heater and a peristaltic pump.
That should do it.
Yeah, it's pretty strong. We create a rod well, so while we're also extracting the water, we're also simultaneously circulating the water to further melt the ice. And then once we collect the water, it goes through our sand filter and then into our collection container.
It sounds like you thought this through.
Just a little bit.
Now, your team has competed before. What were some of the challenges you ran into in years past, and how have you compensated for some of those this year as you compete?
Sure. So 2 years ago, our team faced the issue of over melting the hole. So as they were melting the ice, water was leaking out the side of it and down the test container, making it unretrievable. So to fix that issue, we installed an optical sensor, so that tracks the water level of the ice, of the water as we melt it. And combining that with our rate of penetration into the ice and the time that the pump is running, we're able to estimate a radius of the hole that we melt, so we can also map out the ice as well as the overburden.
Having addressed that, how do you feel about your odds this year of winning?
We feel pretty good. We have a few more issues to work out, but once we get going, I think we'll go strong.
Cool. We'll be rooting for you. Thanks so much for your time. I'll let you get back to it.
Thank you. It's been a pleasure.
Yeah. Let's go over here. We've got one more